Now, if we look at the electrolysis of dilute sulfuric acid, in dilute sulfuric acid is H2SO4. So you have H plus, SO4 2 minus, and because it is dilute, means there is H2O in that. So these are the species present, and species that could get reduced at the cathode. Cathode will attract cations, so H plus, and it will also you'll also have water in it. So we're going to be looking at the reduction of H plus and the reduction of H2O. And when we look at the electrochemical series, so we have the reduction of H plus here and the reduction of H2O. So now the one that's going to get discharged is the more positive one. So it's this one that gets discharged in preference. Species at the anode, you have SO4 2 minus and you have H2O. We're going to look at the oxidation equations, which means that we'll need to be flipping the equations that are from the electrochemical series, which also means that H2O or SO4 2 minus need to be on the right hand side over here, so that when we flip it, these are the reagents, so that when we flip it, they become on the left hand side, because remember, in an equation we always have reagent giving us product. So the reagent needs to be on the left hand side, the product needs to be on the right hand side. So here our reagents are SO4 2 minus and H2O. So means that H2O and SO4 2 minus need to be on the right hand side over here. So let's find the two equations. I have H2O here on the right hand side. But when I look at the equations, I find SO4 2 minus. But SO4 2 minus is on the left hand side, which means that if we flip it to have an oxidation reaction, we find that actually SO4 2 minus is not behaving as a reagent here, it's behaving as a product. So actually we don't have any equation in the electrochemical series where SO4 2 minus is acting as a reagent. And also, if we look at SO4 2 minus, if we look at the oxidation state of sulfur in SO4 2 minus, sulfur is already in oxidation state +6, which is already the highest oxidation state that sulfur can achieve. So we cannot oxidize this further. It's already in its highest oxidation state. So oxidation of SO4 2 minus is never going to happen. So whenever we're going to write the oxidation half equations, you're never going to have an oxidation half equation for SO4 2 minus. So that's why we only have for H2O, and this is the only reaction occurring. So we have the two equations, one which is at the cathode and one which is at the anode. We have the two equations here, and we can add them up here. I have 2 electrons, so I'm multiplying this by 2, and I have H plus and electrons that cancel out, so I end up with H2O giving H2 plus half O2. For here, the electrode potential has been flipped, and so if I find the overall electrode potential, it's 0 plus minus 1.23. That gives me minus 1.23 volts, which is the same for electrolysis of water. Again, you have the mole ratio 1:2. Oxygen is to water. And when we look at the observations at the cathode you have hydrogen gas being produced. So this is colorless. At the anode, you have oxygen gas being produced. So colorless. The volume of gas, if we look at the cathode, we have hydrogen And at the anode, we have oxygen. So ratio of hydrogen to oxygen is 2:1. And when we look at the pH, at the cathode, you see H plus is being used up. So because H plus is being used up, so it gets less acidic. And here at the anode, H plus is being produced, so it's going to get more acidic. So pH at electrode value is going to increase, it gets less acidic. At the anode, it gets more acidic, so pH is going to decrease. Let's see electrolysis of dilute aqueous sodium chloride. Again, inert platinum electrodes. So aqueous means there's H2O. Sodium chloride, you'll have Na plus and Cl minus. At the cathode, you'll have Na plus and water. Reduction equations. So for Na plus is here and reduction of water is here. And the one that is more positive is preferred. So this one is more positive. So it's going to be favored. At the anode, we have Cl minus and we have H2O. So the half equations. So Cl minus, the oxidation and the oxidation of H2O. Now we'll have to flip the equations. So here, the one that's more positive, this one is more positive. It's going to get actually oxidized. So the two equations. So these are the two equations. We're now going to attempt to write an overall equation for these. So we can leave that out, but we can find the overall electrode potential, which is minus 2.06 volts. So as you can see, the electrode potential values are negative, which shows that electrolysis is a non-spontaneous reaction. So we're driving a non-spontaneous reaction to take place by the presence of electricity. Now let's see concentrated sodium chloride. So it's going to be the same equations, exactly the same equations, but here instead of having dilute sodium chloride, we'll have concentrated sodium chloride. So whenever you have concentrated sodium chloride, means the Cl minus is in higher concentrations. So because you have higher concentration of Cl minus is going to get discharged in preference than H2O. So at the cathode, you have the same equation and you will observe the colorless hydrogen gas produced. You'll see bubbles. And at the anode, we'll see the chlorine gas, pale yellow chlorine gas bubbles being produced. You'll smell the pungent odor of chlorine gas. And if you combine the equation at the cathode and at the anode, you end up with this overall equation. And you can see that during the electrolysis, you have OH minus, which is being produced. So OH minus, which means that the pH is going to increase. And because you have also Na plus in solution, you have NaOH, which is produced. So it becomes more basic. So remember, whenever you have a concentrated electrolyte, means that you're going to have the concentrated anion, which is going to be discharged instead of the dilute one. So you can verify your equations and your overall equation.